All right, so next up today, we have Will Cerny, who's joining us from the University of Chicago, where he'll be a rising senior this coming fall. Will has been working with Josh over the summer, and he'll tell us about his project studying the dark matter content of the Carina 2 and Carina 3 ultra-faint dwarf galaxies. Go ahead whenever you're ready.
Great, thank you very much for the introduction. So as Glenn said, I'm going to be talking about some of the most extreme galaxies in the universe called ultra-faint dwarf galaxies. So to tell you a little bit why they're interesting, they're the universe's least luminous galaxies. And when astronomers call them ultra-faint galaxies, they really aren't joking. So in this large image, you're seeing a look at one of these ultra-faint dwarf galaxies, the Leo 4 galaxy from the Sloan Digital Sky Survey. And in the inset panel, you're seeing an image from the Hubble Space Telescope. And if you're not seeing anything there, I don't blame you. They really are that diffuse and low surface brightness, and you really can't pick them up in images. Nonetheless, they're extremely interesting objects to study. Not only are they the least luminous, they're also some of the most metal poor and most dark matter dominated galaxies in the universe. They're also some of the most ancient and most numerous galaxies in the universe. Unfortunately, because they're so hard to detect, we've only been able to detect them as satellites of either the Milky Way, the LMC or the SMC, and of the Andromeda Galaxy. However, by virtue of that proximity, the ones that we can study are resolved into stars, and we can use the kinematics of those stars in these nearby galaxies to study the dark matter content in them. So today in my talk, I'm going to tell you a little bit about how we're doing that. The main takeaway from my talk today is going to be that from the kinematics of member stars within these galaxies, we're able to infer their masses, and it's from those masses that we're able to confidently conclude that these ultra-faint dwarf galaxies are very dark matter dominated systems. So I'm going to talk you through each step of these procedures that are colored here and how we got a result for the Carina 2 and Carina 3 ultra-faint dwarf galaxies' dark matter content. The first thing we need to do is take a spectrum of every single star in the galaxy, in each of the two galaxies, and measure their radial velocities and metallicities. So to measure the radial velocities, we're using red optical spectra from the IMAX spectrograph on the 6.5 meter Magellan-Batta telescope. With these individual spectrum, we're taking the data and trying to match a velocity template of a well-observed star to the observed data. So I'm showing the results of that fitting procedure here. Essentially what you're seeing is the green is the noise and the data, and the blue is the template. And basically we're shifting this template through a range of velocities, trying to maximize a simple likelihood function to find the best fit velocity for each star in our sample. We have about 750 stars that we observed with IMAX. And so when we measure the velocities and plot them in a histogram, we get something that looks like this. Now, this plot is cheating a little bit because we have some prior information, and I'll try to make the case more conclusively in a second, but you can already tell that there's sort of three separate peaks sort of standing out in this data. There's sort of a low velocity peak from 0 to 200 kilometers a second. Those correspond to Milky Way stars, so stars in the foreground that belong to the Milky Way, which are in the field of view of these galaxies. There's sort of a lower peak at around 300 kilometers a second, which will turn out to be the Carina 3 ultra-faint dwarf galaxy. And there's a peak way out at around 480 kilometers a second, which will turn out to be the Carina 2 ultra-faint dwarf galaxy. So as I sort of alluded to before, we took about 750 spectra in total. And so if you're looking at the spatial distribution of stars around these galaxies, there's a lot of stars, and we've observed 750 of them. And we have to figure out actually which stars are part of these galaxies, because when we're taking multi-slit spectroscopy, it's not necessarily true that every star we're observing is part of these galaxies. We do the best we can, but not every star will be part of the galaxy. So we start with data that looks something like this. This is just the spatial positions of all the stars we have spectra for that are of reasonable signal to noise. And the goal is going to be picking out the stars of each of the two ultra-faint dwarf galaxies from these red stars. To do that, we want to leverage as much information as we have available. So the most obvious piece of information we can work with is spatial information. So in other words, how do the positions of stars in these galaxies compare to where you might expect them to be from sort of a previous morphological fit to this galaxy? So we're not the first paper studying these galaxies. There was a discovery paper that went in and used photometric data to characterize these systems. So found their radius, their luminosity, their ellipticities, et cetera. And so we can use that information sort of as a bit of a prior to say, okay, what is the likelihood that a star is part of the galaxy given its spatial position? So among the same data points you saw on the previous slide, we can draw the ellipses which represent the half-light radii of each galaxy. So the radius within which half the galaxy's integrated lights should fall within. And so that's what this pink circle is here. That's the Carina 3 expected location, and this lime one is the Carina 2 expected location. So in each of these panels, I'm going to be plotting a yellow star. So this you can imagine as a single star you're studying, and we're going to look through it. We had to go through the same procedure for every single star in a data to figure out which are likely to be part of the galaxies. So another piece of information we can use is the ones I described on the previous slide. So the velocity in particular offers really strong information about which stars are likely to be members in these galaxies. And it turns out rather conveniently that Carina 2 and Carina 3 have systemic velocities which are well separated from the Milky Way's mean velocity. So if you think back to that histogram I showed, they're kind of well separated and somewhat distinct. So you can sort of pick them out a little bit by eye. That isn't always true, but it happens to be true here. We also have metallicity information from those same spectra. So if we were to take the calcium triplet feature, which we measured the velocity from, and find the equivalent width of each of those lines, that can be calibrated to the iron abundance in each of these individual stars. And so if we were to plot that iron abundance, or in this case, just the equivalent width of the calcium triplet line versus velocity, you can see that there's sort of 3 clusters maybe starting to form. You have that same Milky Way cluster again. You have a sort of signal at low equivalent width, otherwise known as low metallicity, and these intermediate velocities. And then you have, again, the signal for Carina 2, which is at very high velocities and low metallicities again. Lastly, we have photometric information, which we can still use. So in this panel, I'm plotting just a standard color magnitude diagram. So you can think of the y-axis as luminosity and a blue filter, and the x-axis as color. And in black, I'm plotting an isochrone corresponding to an old metal poor stellar population. So you can see that you can use the information provided by the photometry of each star. So here I'm plotting stars that are likely to be members of Carina 3 in pink to figure out whether stars are likely to be consistent with that old metal poor stellar population. And so, we would look through where the position of the yellow star is in each of these panels, and you can imagine that's a lot of information you can use to figure out which stars are members. We can also use information from the Gaia satellite to make this determination easier. So for example, we want to make sure to filter out anything with a non-zero parallax, because those are likely not to be members since these galaxies are too far to have well-measured parallaxes. They're tens of kpc away in the Milky Way halo. And then we can use the proper motions. So since these are gravitationally bound systems, you should expect the stars to have similar tangential velocities, which are sort of reflected in their proper motions. So you should expect the stars that you observe to have clustering in a proper motion space. Once we have all those member stars identified within each of the 2 galaxies, we can infer their masses from their stellar velocity dispersion. So the general picture again is that you have a galaxy moving through space, and the stars in that system have some internal motions. And it's those internal motions, or the dispersion of velocities about these galaxies' mean velocities, that can be used to tell us about the galaxy's masses and therefore their dark matter content. So we use a simple 2-parameter likelihood to separate the systemic mean velocity and the velocity dispersion and constrain those through an MCMC sampling procedure. And so here I'm showing you the results for Carina 2 and Carina 3, where the quantity of particular interest is this sigma RV quantity, the stellar velocity dispersion. And with that value, we can directly constrain the dynamical mass of these systems, because the dynamical mass is shown in this formula down below, is related to the line of sight velocity dispersion squared. It's also related to a couple of constants, one of which I would point out is the radius of the system, because this is really the dynamical mass within the half-light radius. So on to the next slide. To sort of turn those velocity dispersions I showed into masses, we find that Carina 2 has a mass of approximately 1.1 times 10 to the 6 solar masses, and Carina 3 has a total mass of within 1 half-light radius of 2.1 times 10 to the 5th solar masses. And these are preliminary results. This is the first reliable constraint for the Carina 3 galaxy. Previous studies studied both of these galaxies spectroscopically, just like we did. But due to the low number of stars they observed in Carina 3, they were not able to place a constraint on the mass or the velocity dispersion or the dark matter content. Just to compare these numbers, the Milky Way is 0.5 times 10 to the 12 solar masses, roughly speaking. So that's a factor of roughly 10 to the 6 bigger than the mass of each of these galaxies, which tells you how sort of low mass these galaxies are. They really are extreme galaxies. Lastly, we can take these masses and convert them into mass to light ratios by dividing by the luminosity of these galaxies in solar luminosities. So that's what this quantity, the mass to light ratio is. And for Carina 2, we find that the mass to light ratio of the system is roughly 400, plus or minus quite a large number. And Carina 3 has a mass to light ratio of 550. Now, to sort of calibrate how you should interpret these values, a system with a mass to light ratio much greater than 1 can be considered dark matter dominated. So when you see numbers like 405 to 550 for the mass to light ratio of these galaxies, you should think of them as very, very dark matter dominated systems. So they fit in right where our expectations would be for ultra-faint dwarf galaxies. To put them further into context, the Milky Way mass to light ratio is of order 10 or less, which should tell you about how much more dark matter dominated these systems are than their host galaxy that they orbit. To put them further into context, we can compare the results we get for Carina 2 and Carina 3 to the known population of ultra-faint dwarf galaxies, which are plotted here in purple from a review compiled by Simon 2019. As you can see, they lie mostly where you'd expect along the locus of dynamical mass. So this is the y-axis, and luminosity and solar luminosities, I apologize. And they're not particular outliers. And what you can see here are these red arrows. Those are examples of galaxies where we haven't been able to resolve a velocity dispersion. And that was the case for the Carina 3 galaxy before my work this summer. And now, we were able to take one red arrow that would have been there off the plot. And so we've been studying just 2 galaxies, but it's really from this population that we can gain further insight into the properties of dark matter and sort of the distribution of dark matter around the Milky Way. In other words, for example, by studying the entire population of ultra-faint dwarf galaxies and characterizing every single one of them's mass and dark matter content, we can gain a lot more information, for example, about the subhalo mass function or the distribution of subhalos and their masses sort of around the Milky Way, which can tell you a lot about galaxy formation, for example. So in summary, we've constrained the masses of the Carina 2 and Carina 3 ultra-faint dwarf galaxies using the kinematics of their member stars. We find that Carina 2 and Carina 3 are consistent with being dark matter dominated dwarf galaxies. And lastly, we find that the 2 galaxies are prototypical ultra-faint dwarfs and lie nicely on the expected relations between mass, luminosity, and mass to light ratios. Thank you very much for listening, and I'm happy to take any questions.
All right, very nice, Will. Do we have questions about Will's talk? Alex.
I will. I was wondering, since you went back and got more data on these galaxies, did you get enough information to see whether there were any binaries or something that might be changing the velocity dispersions?
That's a really great question. Thank you. Yes, we have plenty of data on these galaxies since we're now the 3rd spectroscopic study of these galaxies. And so while I've kind of omitted some of the details here, when constraining the velocity dispersions for general purpose, obviously a single binary star can greatly affect these results by sort of creating an outlier which will inflate the velocity dispersion. And so as you suggested, you can look to see whether the binaries by seeing whether the radial velocity varies over time. And indeed, we have found that some of the binary candidates identified by the earlier studies are still consistent with being binaries, and so they should be removed for this type of kinematic analysis. The same applies to variable stars in the system, which also have variable radial velocity due to their pulsating atmospheres. So the answer to your question in short is yes, we have been able to look for binaries, and we have been able to identify some stars which are very likely to be binaries and remove them from this determination.
Thank you, Will. Madeline, do you have a question?
Yeah, I just wanted to remind myself, so of your initial kind of block of stars that you were sorting into, going into different dwarf galaxies, do you have a count for like how many stars were actually in each one?
Yeah, thank you for the question. So in Carina 3, so the one on the right I'm showing here, has a total of 8 stars. So we're still working with a very small sample, but nonetheless are able to resolve, are able to resolve a non-zero velocity dispersion, so one that isn't consistent with 0. For Carina 2, we have quite a few more to work with. And in total, we have close to 30, maybe a little more than 30 stars to work with that are likely members.
Wow. So following up, sorry, Glenn, if this is taking too much time. So I guess where does is there a line between like purely dark galaxies and kind of like where that shifts into ultra faint dwarf galaxies? That might not be totally related to your
So is your question, is there something that defines ultra faint dwarf galaxies just in general?
Sure, yeah.
Sort of the answer to your question is no. I think the definition of what constitutes an ultra faint dwarf galaxy versus a classical or normal dwarf galaxy versus even a massive galaxy is sort of very arbitrary. I don't think there's really any clear physical reason to separate some of these ultra faint dwarf galaxies from their sort of more massive dwarf galaxy counterparts. But yeah, it's somewhat arbitrary, but the literature has sort of adopted a particular definition based on the luminosity of the galaxies, which we sort of use to artificially distinguish them.
Thank you very much.
All right, wonderful. Let's thank Will again.